Good evening. My name is Kawiga Salem and I'm here to present you the local search algorithms and adversarial search. I begin by defining the local search algorithms, which are just algorithms which mainly focus on the final goal, not specifically on the path taken to find that goal. We are having various algorithms. We shall begin with the hill climbing. By definition, hill climbing algorithm, it's an iterative local search algorithm for optimization problems. It seeks the highest point in a search space, but it may get stuck in the local optima. It gets stuck in the local optima because um, it might get a solution which we see it's a better one, but then in actual sense it's not the best solution for the search space. For example, let's say we are having this as the current state, as the current node, and it has various nodes like this and this. So what the hill climbing does, it comes and checks these nodes, what has the highest value. If this one has the highest value, it means it be iterated over before this. The process you continue like that. We shall now check the nodes of this current node, pronounce the current one. If this one has the highest value, to be iterated before we go to the next one. So it will keep like that until you reach a point and find that you're having a steep ascent like this you're seeing. Yeah, so that's the hill climbing. Then let's go now to the simulated annealing, which is another algorithm for the local search. By definition, it's a probabilistic algorithm that accepts suboptimal solutions in order to avoid the local optima. Yes, the simulated annealing helps avoid the local optima because it takes random values, doesn't consider selecting the neighboring node, it takes on the random values. For example, let's say this is a random value and this is the current state, so it will come and check if this random value is less than the current state. If it's less than, that means to be now accepted as the current state. That's what it does, and the process will continue like that. And this is our graph. Then we are having another algorithm, the genetic algorithm. It's a heuristic search, mimicking a natural selection. The key techniques here, we are having commutation, crossover, and selection. We did this in biology in high school, whereby we are using the crossovers in biology to find the offspring of a certain parent class. We get various parents from a certain population and then cross them over to find a given pair of offsprings. Then improving usability with AI and explainable, responsible, and explainable AI. We know that responsible, it mainly focuses on the fairness and transparency in decision making, and then explainable AI mainly focuses on AI decision making processes manageable for users. For example, in responsible AI, let's say we are taking a certain relief to a certain community. It means that for this, it will make sure that this relief is equally distributed to that community, and the model will now be responsible in that sense of responsible AI. And then in responsible AI, it mainly focuses on decision-making processes to make them manageable for users. For example, we are having a model that selects the best route in a certain town. That means it has to make sure that the route chosen it's the best for everyone in that town, considering various factors like distance and time. Then research, and research is mainly used in a competitive scenarios where two agents having conflict goals. For example, in a chess, in a tic-tac-toe, those are two games whereby we can use adversarial search. It takes up two agents, let's say the max and the min, in that the min focuses mainly on minimizing the scores of the max, and the max also focuses on maximizing the scores. This is specifically an example. Let's say you're having a tic-tac-toe. You know that tic-tac-toe, it can either be an X or an O. So let's say the max starts and then followed by the min, something like that. So the scores at the end will be determined by how the two have performed their games. These are the scenarios you're having, whereby you're having the marketing competition scenario and the cybersecurity scenario. The very many scenarios in the research. Even playing chess is a scenario in the research. Having various algorithms in the research. For example, having the min-max algorithm, which mainly focuses on two players, and then the terminal solutions. In the terminal solutions, how we get the answers, we come and consider the for the min. It means we shall consider the terminal solution with the least value. For this case, it's the 3. So I take up the 3. So the 3 come here, and for this case, I take up the minimum value, which is the 2. It will come here, and same applies this. Then for the max, of course, looks be taking the maximum value from these given values, and the maximum pair is a 3. So the 3 will be put here. Then next slide, we are having the expect min max algorithm, which is just like the previous slide, but for you, what it does, it mainly in the terminal solution, it takes the average of the numbers. Yeah, I would say assume you're having assume you're having a 5 here, we are having a 5 here, and a 6 here, and a 2 here, and a 1 here. What it does, it takes the average of these. So 6 plus 5, it should be, assume this is also a 6, take the average, which is a 6, it will come let's say here you have a 1, 2, here we're having a 3, here we're having 4, here we're having 5. Okay, it will just takes up the average of these two numbers. Add these two, you will get 8. We put here 4, like that. Takes up the average, and then what follows will be the same as the min max algorithm. Then next line is the AB pruning, the alpha beta pruning. The alpha beta pruning is also like the min max algorithm, but for it to prunes, it doesn't let us waste time on a node that will lead us to, like wasting time. So what it does, it keeps on assigning certain values to alpha and beta, interchanging them, and when you reach a point and find that you'll be wasting time on a certain branch, that branch is pruned out. So this is what alpha beta pruning does. And then adversarial machine learning, this is just it's a technique in AI that attempts to mislead the model to give wrong answers, in that those wrong answers can be used to find the better solutions on how to guide the machine model from making those mistakes. For example, an attacker subtly alters images so that a model misclassifies them, even though they appear unchanged. For example, let me say a model was trained that this is a dog, then it comes out that this model is given this dog model is given another sound like a cat sound. So it means that by the end of making that sound, the cat sound, this machine model might say this is a cat, and when in actual sense it's a dog. Understand? So just by adding in that voice, the machine model misclassifies this from being a dog to a cat, just because they added a certain sound for the cat. And the relationship between the adversarial machine learning and adversarial search, the key strategy, we shall focus on the key strategy. Just as adversarial search anticipates opponent moves, adversarial machine learning accounts for potential attacks on models, just like I've been explaining that up. Thank you for your time. Bye.